So, Newton did a lot of experiments on the rate of cooling of hot objects and discovered that the rate of cooling depends on the temperature difference between the object and the surroundings. So, you see here, so in the cooling process, generally the cooling is done actually by radiation and some cooling is done by convective heat transfer. So, for convective heat transfer we do not have any mathematical formula, because that is actually in convective heat transfer there is a heat and mass transfer. So, there is not exactly for a mathematical formula. So, we believe that convective heat transfer also the rate of heat transfer will be proportional to the temperature difference between the object and the surroundings. And so, largely we will assume that this heat transfer, that the cooling is taking place because of radiation, and we can justify this with our Stiefel-Boltzmann's law. So, let us see what was the experimental finding of Newton's. So, thus Newton experimentally found that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings. So, important point that the temperature difference is not initial, but the instantaneous. So, d theta by dt is proportional to surrounding temperature is theta, suppose S minus theta. So, this is what Newton's law of cooling is. So, now suppose this is theta, d theta by dt is proportional to this. So, in order to see how temperature varies, let theta naught be the temperature of a body at time t. So, theta naught be the temperature at time t, not t, but at t is equal to 0. The surrounding temperature is constant and is equal to Ts. So, now let the temperature of the object be theta at time t. So, let its, so we have d theta by dt is equal to minus k times theta surrounding. So, the temperature difference will be actually theta naught minus theta s. So, theta naught is greater than theta s. Now, the negative sign indicates that the temperature decreases with increase in temperature. Negative sign indicates that the temperature decreases with increase in time. This is what increase in time, this is what cooling means. So, now you see here I have d theta by theta, this is initial. So, instantaneous theta is only theta minus theta surrounding is equal to minus k dt. So, suppose 0, if time is 0, that means theta is theta naught, if time is t, theta is theta. If I integrate it, I will get this ln theta minus theta s from theta naught to theta is equal to minus kt. This on further gives ln theta minus theta s by theta naught minus theta s is equal to minus kt. So, now let us see this is our relation which further will give theta minus theta s is equal to theta naught minus theta s e raised to minus kt. So, we have here again further theta is equal to theta s plus theta naught minus theta s e raised to minus kt. So, thus you see the temperature is decreasing exponentially. So, thus you see if I plot the curve of temperature variation, that is how the temperature theta of a hot body placed in a uniform surrounding, initially the temperature is, suppose I say theta naught, then it decreases and after a long time it decreases to 0. So, this is an exponential curve, that is theta s plus theta naught minus theta s e raised to minus kt. This is how the temperature of a hot body will vary with time, when we assume that the energy is radiated, is lost by radiation and or natural convection. We believe that it is a natural convection or radiation. Now, let us see that how by Stephen Boltzmann law we can derive the Newton's law of cooling. So, this is our hot body at a temperature initially theta naught, and it is placed inside an enclosure whose temperature is theta surrounding. So, what happens? It emits radiation as well as it absorbs radiation. So, consider a body, let us assume it is a black body. Consider a body which is initially at temperature theta naught, placed in an enclosure at a constant temperature of theta s. So, theta s is constant and theta naught is changing. Initially it is very high. So, theta naught is higher than theta s. So, this is what it is losing energy. So, let us write down the heat balance equation. So, heat balance equation for the body. So, you see the amount of energy radiated is the amount of energy absorbed. So, you see here dq by dt, this is the rate of net heat loss. So, net heat loss is equal to, let us see, sigma A T, suppose its temperature is theta naught. So, let it be at some time it is theta. So, theta to the power 4 minus, this is sigma A theta s to the power 4. You see, this is the rate of cooling. So, cooling means, or you can say it is the rate of, suppose energy being radiated. So, this is the energy being radiated, this is the energy being absorbed. So, cooling is because of energy radiated, and this is the energy, the rate at which the energy is absorbed from the enclosure. So, dq, when you take some amount of energy dq, then temperature, when you radiate it, then temperature decreases by mass into specific into the decrement in temperature. Suppose decrement in temperature is denoted by d theta, and this will be some sigma a theta to the power 4 minus theta s to the power 4. Now, let us denote the excess temperature to be theta. So, we can also write the difference in that will be also theta. So, now you see here minus ms d theta by dt is equal to sigma a. Theta means something theta s plus theta. So, theta s by 4. So, I have minus ms d theta by dt is equal to sigma a. Now, you can take this theta s common. So, we have theta s to the power 4. So, 1 plus theta by theta s to the power 4 minus 1. Next, you see this is minus m into specific heat into d theta by dt is equal to sigma a theta s to the power 4. Take the binomial approximation, 1 plus 4 theta by theta s minus 1. So, here I assume that this theta is very less than theta surrounding. So, theta is the temperature difference. If the temperature difference is very less than theta surroundings, then only we can use this approximation, otherwise not. So, now further you see d theta by dt becomes sigma minus sigma a theta s cube by ms into this is again 4 here and then theta. So, you see this quantity is constant. So, d theta by dt is equal to minus theta. So, this constant k, and what is theta? The temperature difference I have assumed, that is here you theta is actually this is theta naught. So, this is theta is equal to theta s theta naught. So, here you see theta naught is equal to this theta s plus theta. So, you see this theta is the temperature difference, theta naught minus theta. So, theta naught minus theta surrounding. So, thus the Newton's law of cooling is established by the help of Stefan-Boltzmann law. Now, let us check the validity, that you see this theta must be less than theta s. So, let us see in our common language, suppose this theta naught is at 100 degree centigrade and theta surrounding is at 27 degree centigrade. So, let us see whether I can apply this approximation, because theta is very large than theta. So, you see the temperature difference theta is the order of nearly 27, 100 minus 27 nearly 70, I can say, suppose this is 70. So, this is 70 and theta s, it is expressed in actually Kelvin. So, theta surrounding is 27, 273, that is nearly 300. So, 70 by 300, that means if the temperature difference is something 27 and 100, then the law will not be that much accurate. If this is suppose 40 degree or 60 degree, that means suppose it is 30 degree temperature here, 30 degree temperature here, and then you see it is 1:2, so it is more accurate. That means when the temperature difference is very small or not very large, then this formula can be readily used.